we can start the next presentation of this afternoon on the third session of the course in cohomology of Leibniz algebra by Friedrich Wagemann. You can start.
Thank you for the introduction. So this will be my third lecture. So we talked yesterday about Lie algebra cohomology, and so Lie algebra cohomology is also called Chevalley-Eilenberg cohomology, and it is homology theory on which comes with a co-chain complex here, based on the exterior products of the Lie algebra, and with a co-boundary operator, which goes from CP to CP plus 1, like cohomology, and which is written like this. And I just recall this in order to show you the difference to Leibniz cohomology. So now H Leibniz algebra, then the Leibniz cohomology complex will be built not on the exterior powers, but on the tensor powers of G. And so M H I module. And so this is then cohomology with values in M. And so I already told you that what Jean-Louis Loday found in the early 1990s is that the Chevalley-Eilenberg co-boundary operator lifts to the tensor complex, yeah? And this is exactly what the co-boundary I'm now writing down is all about. So the co-boundary operator for Leibniz cohomology, unfortunately, I will give it the same name. All my co-boundaries operators will be called D. I hope this is not too confusing. And so now I take a C, which is a P co-chain on H, sorry, with values in M. And so on the one hand, you can have this term here, and now what Loday found is that you have to put the bracket, yeah, not in front, but in the J's spot, yeah. Actually, what happens is for right Leibniz Lie algebras, you have to put it in the I spot, but I'm working with the left Leibniz algebras, and for left Leibniz algebras, you have to put it in the J spot. And this is the J spot, and this eats up the sign, yeah. So this -1 to the I is eaten up by the fact of transferring the bracket from here to the J spot. And so it should be, should be I. Okay, and so again, over 1, here again. And then these are the bracket terms, and then there are action terms. And these action terms, they have the same sign. But the only difference is now you have a bimodule here. M is an H bimodule. So you have this left operation and the right operation I talked to you about on Monday. So you will only take for the P first elements this left operation, and then you put in a term with the right operation. Is this visible? Yeah, this is last. This is the term with the right operation, and the sign is p plus 1. Yeah. So let me explain this sign. What is this sign? In case the module is symmetric, meaning that the right operation is the opposite of the left operation, you have to have the same sign as here. Yeah. And so putting it on the other side would give p plus 1. Yeah. And this would be the sign here because I didn't put it correctly. You see here it was minus 1 to the I, so it's I plus 1. Okay, this is the Leibniz co-boundary operator, and then Leibniz cohomology of H as well as an M is just the kernel of P from CLP to CLP plus 1 divided by the image of P going from CLP minus 1 to CLP. Yeah. So these are the Leibniz cohomology spaces I'm going to talk about. And so
may I please interrupt for a moment?
Yes, go ahead.
So in the first term of the co-boundary operator, this bracket xi xj is on the jth spot.
Yes.
Do you actually mean that it is between xj and xj plus 1 or after xj plus 1?
It is between xj minus 1 and xj plus 1.
Yes, xj minus 1, xj plus 1. Not
exactly.
After j plus 1.
No. Yes. Yeah. So I see I see your point. This is not exactly the J spot because I took out the xi before. Yeah. I mean it is between xj minus 1 and xj plus 1. Thank you.
Okay. Thank you.
Yeah. Other questions up to this point? Okay, then let me go on. Yesterday we talked about the interpretations of low degree terms in Lie algebra cohomology, and so I will not do this in detail for the Leibniz cohomology, but let me just explain the changes you have to make. So, in fact, the co-boundary operator going from CL0 to CL1 sends now, so CL0 is just M, and M to the map which sends X in H to X acting from the right on M. Yeah, this is because only this last term here is visible. It is non-zero in this term. Yeah, and so this means that the H0 is only right invariance. Yeah. So now you have an operation from the left and from the right. So you have to say invariance with respect to which action. It is only the right action. Yeah? While in the Lie algebra case, it was the only operation we had, and we wrote it from the left. Okay, and for example, if M is antisymmetric, yeah, I recall that antisymmetric means that the right action is trivial. Yeah, then obviously, this gives just M itself. Yeah. So, this is one thing. And for example, now let us write also the co-boundary operator from CL1 to CL2. This sense. So now, df, let's take, this is on HM, exactly like in Lie algebra theory. And df of x1, x2 is now f of x1, x2, maybe with the minus sign, plus x1 acting on f of x2 minus plus f of x1 and acted on from the right by x2. So you see, this is almost the same expression as in Chevalley-Eilenberg cohomology, but the only difference now is that I don't switch elements. Yeah. So in Chevalley-Eilenberg cohomology, it would be f evaluated on the bracket x1 dot f of x2 minus x2 f dot f of x1. But here I don't switch brackets and I use the right operation, and so I have a plus sign. That's the only difference. Yeah. And so, for example, when you have H equal to G Lie algebra and M equal to MAS, symmetric bimodule, then this gives you just that the HL1 of GM is just the HL1 of the H1 of, in fact, of G, yeah, with values in M. Yeah. And so now the M here is a little bit ambiguous. When I have a symmetric bimodule, I can look at it as being just a left module over this Lie algebra. So now, one can go one little step further, and actually, what is always true is HL1 of HM is equal to H1 of H Lie of M. Yeah, because, oh, I'm sorry, not for every M, for the trivial module. Yeah, because for the trivial module, these terms are 0 here. Yeah, and so you only have the bracket term, and the bracket term is the same as for H or for H Lie. And what happens is the Leibniz ideal, the ideal of squares, acts always trivially, yeah, from the left, like H acts trivially from the left. And this is all. This is true because of the identity the left operation has to satisfy. Yeah, this is the identity, and now put x equal to y. And this gives that squares always act as 0. So this shows that HL1 on H is just HL1, H1, yeah, the Chevalley-Eilenberg H1 on the Lie algebra canonically associated to H. And we have seen that this is HV over HV bracket with HV. The H1 is only this. And now, as I don't want to lose too much time, I'm not doing the case of L2, HL2, exactly as in the case of Lie algebra, classifies extensions, yeah, but Leibniz extensions of H prime M, yeah, and HL2 of HH classifies, yeah, governs deformations, formal deformations of A. Yeah, exactly the same as we discussed in Abdel-Nasser Makhlouf discussed in his lectures. In case HL2 of HH is 0, every deformation of H, every formal deformation of H is equivalent to the trivial deformation. Yeah, and the theorem I'm going to talk about more precisely on Thursday and Friday, which I proved together with Jörg Feldfuss from the University of South Alabama, shows that for semi-simple Leibniz algebras, this HL2 of HH is always 0. And so all of their formal deformations are equivalent to the trivial deformation. And so, as I told you already yesterday, the first cohomology computations have been on the Leibniz cohomology of Lie algebras. Yeah? In the beginning, Loday and also Pirashvili were only interested in the Leibniz cohomology of Lie algebras. Yeah? And as I explained to you on the first day, this comes from from the history of the subject, because Loday found Leibniz algebras as incarnation of the hindrance of periodicity in algebraic K-theory. Yeah? And in this context, he wanted to apply it only to GLA, to the Lie algebra GLA, yeah? And not to any Leibniz algebra. Yeah? So these first cohomology computations were always for Leibniz cohomology of Lie algebra. So for example, there are computations by Pirashvili, but also by Jean-Louis Loday. Yeah, Loday had a very interesting paper I cited where he computes the Leibniz cohomology of the Lie algebras of formal vector fields in n variables. Yeah? And for example, we used then this together with Alessandras Rabetti to go from these computations for the Leibniz cohomology of the Lie algebra of formal vector fields to the Leibniz cohomology of the Lie algebra vect S1 of, oh yeah, this is not visible. Vector fields on the circle. Yeah. So this is a very complicated computation, and actually we couldn't do it up to the end, this computation. We only managed to compute the diagonal of Leibniz cohomology of vect S1. Yeah, the whole Leibniz cohomology is much bigger, and for the moment as to my knowledge, unknown. But nowadays, there are also cohomology computations for I think your mom does also computations for Lie algebras, Leibniz cohomology of Lie algebras. That's for the Euclidean or pseudo-Euclidean Lie algebra. And then Loday also has other papers nowadays on the subject, the cohomology of the Lie algebra of affine vector fields, things like that. So I cannot talk about all of them, but just to tell you some names and to say that there are many cohomology computations already available. Yeah? So, but mostly, as I said, mostly cohomology computations of the Leibniz cohomology of Lie algebra. While together with Jörg, what we do is Leibniz cohomology of Leibniz algebra. And so one of the lemmas which I find the most interesting about Leibniz cohomology theory is that Leibniz cohomology theory is very close to Hochschild cohomology in some sense. Yeah? And in the sense that you can always switch an argument from the module side to the from the module side to the module side. Yeah, so now what I want to say is you can always interpret n cohomology of H with values in an anti-symmetric module as n-1 cohomology of H with values in a more complicated module. Yeah, and the more complicated module is Hom HM, but now seen as a symmetric module. Yeah. So this is anti-symmetric. And this is symmetric. And so this lemma is a very fundamental property about Leibniz cohomology, and the corollary is that if given H, if all HL1 of H of M is 0 for any bimodule M, then HLN of HM is 0 for all M bimodule and all N. So in some sense, it is the HL1 which governs all the cohomology. And this corollary is also true for Hochschild cohomology. So there is some deep resemblance between Hochschild cohomology and Leibniz cohomology in the sense that it's based on the tensor complex. This is an explanation. Okay, so I give the proof of the lemma, but I will be a little bit elliptic. The full proof is written in my lecture notes. So first of all, HY module structure, H. Actually, we don't need a bimodule structure because what we are saying is we make this a left module, for the Leibniz algebra H, and then we extend it as a symmetric bimodule, yeah, meaning that the right operation is the opposite of the left. So I only have to give a left module structure on this home space. And what one does is exactly as always. Yeah. This is either I act on the outside or I act on the inside with the minus sign. Yeah. This is the definition of the module structure. And now I have to show that it satisfies the left module identity. So for this x, y, and z is x, y, and here I can as M, as this left operation on M satisfies the left module identity, I have here that this is x dot y dot f of z minus y dot x dot f of z, and here behind here I can apply the Leibniz identity to say that this is x, y, z. This is equal to this minus one part of the equation, and the other part is x dot y dot f of z. So x dot this is x dot y f of z minus y dot f of x z. And this is then x dot y z minus x dot f of y z minus and now for the other term, I just exchange x, y, everything I wrote here. Just change y, wrote. And see that this one, it goes with that one, and this one, and here I have this one, that one, this one, and so I only have to see that those cancel out and those out because I take the negative of this line. So this cancels. This one, that one cancels. Yeah. So I have an action. Yeah, you can read this computation also in my lecture notes. Yeah, it's maybe easier to read on a sheet of paper. So this shows that the Hom HM is, first of all, a left H module, and therefore I can consider it as a symmetric H bimodule. Okay, and then the maps defining the isomorphism star are induced by phi going from CLN HM to CLN 1H from HM. And so what you can do, and the only thing you can do is you send co-chain C to the map which assigns to X, the map which assigns to assigns to X1 n minus 1, the map which assigns to X, C of, and I put it in the last variable. I have a map in the other direction. Is this visible? Okay. Yeah, this sends C to the map which sends X1, Xn to C of X1, Xn minus 1. So what I'm not going to show to you is that these two maps are compatible with the Leibniz coboundary operator. Yeah, that these are chain maps. Yeah, maps of chain complexes. This computation is also done in the lecture notes, and I invite you to read it. So this shows then the lamp. So this is what I mean by swapping an argument. Yeah, I will use the term swapping an argument to speak about this manipulation. So as a corollary. I didn't write it down. As a corollary, we can do this, for example, for trivial module. So H, L, N, H, K is isomorphic to H, L, N minus 1, H star. But one has to pay attention here. K is the trivial module, so it is antisymmetric and symmetric, as you like, because both left and right operations are 0. But now here I take H star, yeah, which is actually a bimodule with non-trivial left and right operations, and left operation and right operation which do not have anything to do with each other in general. Yeah, but I don't take this bimodule. Yeah, I take only the left module of H star, and then I extend it to a bimodule as by putting right operation equal to minus the left operation. This is why I put it as. Okay, maybe you have questions so far. Okay, this this ends the very basic and elementary part of these lectures, and now we are going to do some little more advanced stuff and talk about spectral sequence. I will not explain to you what a spectral sequence is. Spectral sequences in Leibniz Sohomology. Let me say just one sentence about what a spectral sequence is. Every time you have a co-chain complex, you want to compute cohomology, in general, this is a very difficult task. And so you try to develop tools to do this. And so extra structure can simplify this problem. And so the extra structure which leads to spectral sequences is the filtration on the co-chain complex. And every time you have a filtered co-chain complex, then you have a spectral sequence which in the very first step takes the associated graded complex associated to the filtration. And then the differential you had on your co-chain complex induces differential on the first on the graded complex and then on the higher pages of the spectrum. And so what you hope for is that this cohomology of the graded complex is easier to compute than the cohomology of your co-chain complex you started with. But I cannot introduce to you spectral sequences in detail, otherwise this would be the end of my lecture. So there are two types of spectral sequences which I want to talk about in Leibniz cohomology. So the first type is the spectral sequences which are related to the comparison of Chevalley-Eilenberg and Leibniz cohomology. And so when you have and here Leibniz cohomology of Lie algebra. So when you take a Lie algebra G and G module M, you can look at it as a Leibniz algebra, left and right Leibniz algebra, and M, you can look at it as a symmetric H bimodule. And you can ask yourself which links are there between the Chevalley-Eilenberg cohomology of G with values M and the Leibniz cohomology of G with values in MS. And so when you think about this a little, and all I'm going to talk to you about here in this paragraph on spectral sequences in Leibniz cohomology is due to Pirashvili. What we did in our paper with Jörg is we translated what he did in homology, we translated it into cohomology. So this is not very, not very new or interesting, but it is powerful, yeah, and because this led us to showing the theorem you have the tensor complex of G, which has the exterior complex of G as a quotient. This is a quotient. And so it induces an injection, injective map of complexes from Chevalley-Eilenberg complex of G of M into CL G of MS. And so this injection here is not an isomorphism, yeah, because in this morphism you have the difference between tensor powers and exterior powers. Yeah, so they are not the same, and so this is not an isomorphism. So you have a quotient complex which measures the difference between these two cohomologies. Quotient complex. This cohomology is denoted relative cohomology, G M, measuring the difference between H M and H L. And how does it measure this difference? Yeah, every time you have a short exact sequence of complexes, yeah, because this is what you have here. You have an inclusion of a subcomplex, and then you go to the quotient. This gives you a short exact sequence of complexes. And every time you have this, general homological algebra gives you a long exact sequence in cohomology. Yeah, and in this long exact sequence, you have Chevalley-Eilenberg cohomology, Leibniz cohomology, and then this relative cohomology. Yeah? And so in this sense, it measures the difference between these two cohomologies. This is one ingredient. The second ingredient is you can swap an argument, yeah, as we just saw it. Yeah. And take cochains on G with values in the trivial module, and then swap an argument from the Lie algebra side to the module side. Yeah? So you get cochains of one order less, yeah, but with values in G star. Yeah? This is exactly what we had in this corollary up there. Yeah? And so because you have here cochains of one order less, you have to readjust the degree of this complex in order to make it a map of complexes, yeah, meaning preserving the degree. Yeah? This is why you have this degree shift here. Yeah? And so there's also, this in fact is an inclusion. Yeah? Why is it only an inclusion? Here, the cochains are anti-symmetric in all the arguments. Yeah? But because here, they're not anti-symmetric in all the arguments, only in the first arguments here, but not with respect to the last argument. Yeah? So here, So this is only an inclusion. This is not an isomorphism. And you again get a quotient complex whose cohomology is called HR of G. Now there's no module here. Yeah, there's no module here. So it's only depending on G. Yeah, and whose cohomology measures the difference and now it's between H G with trivial values and H G with adjoint values. Oh, it's not that. So these are the two ingredients. And what Pirashvili does is construct a spectral sequence. And in case you want to know how this is constructed explicitly, please look in either in Pirashvili's paper in the homology context or in the cohomological framework in our paper with your friend. So we construct a spectral sequence, let's say for finite dimensional G. We also have the E2 term for infinite dimensional G, but it's a little bit more complicated. So let me simplify here. Whose E2 term is E2 of PQ, HRP of G, tensor HLQ G of M S, and converges to H relative. Yeah, you know, so you see this relation between the cohomology of G with values in M and Leibniz cohomology of G with values in MS is quite complicated. Yeah, the relation is given by this cohomology space, which measures the difference. Yeah? And we only have a spectral sequence converging to this cohomology space, yeah? Which has this E2 term. Yeah? And so what is very frustrating is that in this spectral sequence, the cohomology we want to kind of express, yeah, comes in the E2 term. So it's a very tricky problem. Yeah, but what Pirashvili already showed is in some situations, you can use these tools in order to show that cohomology vanishes. Yeah, and so one cohomology vanishing situation is if all Chevalley-Eilenberg cohomology is 0, then also all Leibniz cohomology is 0. Okay. So the proof is also kind of tricky. It goes by induction. And so you use induction to say these first cohomology spaces, yeah, H. So you are aware of the fact that the difference between tensor product and exterior product plays only a role starting from degree 2 on. Yeah? In degree 0 and in degree 1, there's no difference between tensor product or an exterior product. So from the hypothesis, you already have that HL0 and HL1 is 0. Yeah? This you put into your spectral sequence here, and you have vanishing for the E2 term in some spots. Then, therefore, you can express your relative cohomology. And then this you can reuse to go one step further in the vanishing of HLG of MS, which you then re-inject in the spectral sequence. So it's a tricky process, yeah? but it works. And actually in our paper with Jörg, we also have a more refined statement, yeah? Where you put here, if all the P are equal up to a certain N, then in, yeah, you can say, and so on, yeah. So, but that did not talk about this refined statement. That actually you can also show that the contrary, the converse is also true. So you can play with this a bit. But okay, this is one ingredient. Maybe you have questions here.
I see there are questions in the chat. I think instead of H on H bimodule, it is a G bimodule. Yes, 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 you're right, Prince. Thank you. And I think I corrected it afterwards.
So this is one tool, and we will only use the theorem 7.1 in what I'm going to talk about. Yeah, not the spectral sequence detail. Yeah. And then there's a second spectral sequence, the Hochschild-Serre spectral sequence. And this is also a very interesting discussion, because in Lie algebra theory, there's a very readable paper of Jean-Pierre Serre and Gerhard Hochschild. So Hochschild-Serre, where they consider a situation where you have an ideal in a Lie algebra with a quotient Lie algebra, and so this is Lie, and this is an ideal in G. Yeah, so this is the only place in these lectures where I will use H for an ideal in a Lie algebra. In all other places in these lectures, H will be a hyperparameter. But here, it is an ideal in the Lie algebra G. Yeah? And then you have a filtration on the cochains of G with values in some module, and get a spectral sequence with E2 term HP of HP of Q with values of HQ of H. Yeah, and converging to HG of N. And this is kind of the most easy spectral sequence you can imagine, because you have cohomology of your constituents, yeah, and the E2 term is just the cohomology of the constituents, and you converge towards the cohomology of the whole thing. And unfortunately, in Leibniz cohomology, you don't have anything of this type. The best you can get is when you have a surjection, yeah, surjective homomorphism of Leibniz algebras. And and M Q bimodule viewed as an H bimodule via the SMAP pi, yeah, then you have a subcomplex. You have an inclusion of co-chain complexes CL of Q M into CL of H M, but with M seen as a bimodule via pi, and you get a quotient complex as before. And this is so relative homology with respect to Q. And you have to shift the degree. Degree shifted. And so therefore you get a long exact sequence, which goes like this. Yeah, and so the degree is shifted here. So this is an H0. And so on. Yeah. So this is kind of the best you can have here. This relative cohomology telling you the difference between the cohomology of the quotient Leibniz algebra and of the Leibniz algebra itself. And I will come to an end here. Yeah, just 1 minute. So let's take finite dimensional Leibniz algebra also, again, just in order to have a nice expression of the two term, and let I be an ideal in the Leibniz algebra H with quotient Q, and this is the net I. Yeah. Then suppose that I is included in the left center of H. Yeah. So meaning bracketing with elements of I from the left gives 0 on H. And let M be let's say symmetric Q bimodule. Viewed as an H bimodule via I, then there exists the spectral sequence. And once again, this spectral sequence is due to Pirashvili in the homology framework and to us in the homology framework, but it's not a big deal to develop the homology framework. Converging to relative cohomology, and with E2 term HL UIS So the only thing I want to say in conclusion is this is unfortunately the best we have in terms of a Hochschild-Serre spectral sequence for Leibniz algebras, and it is much weaker than the Hochschild-Serre spectral sequence on Lie algebras, yeah, because we are not even converging to the good thing, yeah, we are not even converging to the cohomology of H, which we want, yeah, in the Hochschild-Serre spectral sequence, we converge to the cohomology of the whole thing, This is not the case here. It's even worse. Yeah, it's even worse. The cohomology of the whole thing is coming in the E2 term. Yeah? So it's kind of very tricky, very weird setting, but this is the best we have. Yeah. Okay, this is kind of the presentation of the tools, and I will stop here. Tomorrow we will use these tools to compute, first of all, the cohomology of Leibniz cohomology of semi-simple Lie algebras. This is due to Pirashvili and Loday, and then go on to compute the Leibniz cohomology of simple Leibniz algebras. And this will be Thank you for your attention and see you tomorrow. Questions?
Okay. Thank you very much for this interesting presentation. Are there any questions or remarks? No question? Remarks?
Thank you. So I have some question about the correspondence with Leibniz algebra and Lie algebra, in the sense that if we have H Leibniz algebra, we can have H Lie, the corresponding Lie algebra. But the converse is true, in the sense that if we have one Lie algebra, there is a Leibniz algebra that the H Lie of this Leibniz algebra is equals to the Lie algebra.
Maybe I don't understand exactly what you mean.
So you want, given a Lie algebra, you ask whether there exists a Leibniz algebra such that what?
If we have,
does there exist H such that, yes, tell me.
Such that if we have a Leibniz algebra, the H, for example, so it exists H Lie algebra.
H Lie algebra.
Uh-huh.
What is an H Lie algebra?
H indexes Lie, as you said in your talk.
So given G, does there exist H such that for all other Leibniz algebras H prime, there exists?
Exist. So it's not the same. I think is there a bijective correspondence with Lie algebra and Leibniz algebra set?
So if you just ask whether there's a bijective correspondence between Lie algebras and Leibniz algebras, the answer is no. Yeah, and we have seen that Leibniz algebras are very much richer than Lie algebras. Yeah, because to any Lie algebra, yeah, we have seen this, and any G module you can associate a Leibniz algebra which is not a Lie algebra. Yeah? So, and on the other hand, every Lie algebra is also a Leibniz algebra. Yeah, so this class of Leibniz algebras is much bigger than the class of Lie algebras. Yeah,
Okay.
actually,
yes.
Yeah, this is kind of not a good thing. Yeah, so in some situations, this means that the theory of Leibniz algebras is much cruder, yeah, much less restrictive, and so much less rich than the theory of Lie algebras, yeah, because it's so much bigger and everything is blurred. Yeah, I don't know whether this answers your question.
Yes, yes. Then the converse of last theorem on if the Chevalley-Eilenberg cohomology is null, so the Leibniz homology is null too.
Yes.
So the converse is not true.
The converse is true, actually.
Okay.
Yeah, the converse is true, and is please read the proof of it in our paper. It is yeah. This is a remark on page 14. Yeah, this is trivially true.
Okay. Okay. Thank you. Thank you.
I have also one question, please.
Yes, go ahead.
You talked yesterday that cohomology gives some information about the algebraic structure of the algebra. Is it the same thing with homology? Do we have some equivalent theory about homology of the algebra as well?
Yes, yes. So homology also gives you informations about the structure of the Lie algebra, and kind of cohomology is a little bit more related to modules. Yeah. So there are some subtle differences. Yeah. For example, the H2 in homology is related to the center of the universal central extension, while H2 with an upper index in cohomology has also to do with extensions. Yeah, but there are some links between homology and cohomology, and for example, for unimodular Lie algebras, yeah. For unimodular Lie algebras, you have duality between homology and cohomology in some sense. This is, for example, explained in a paper of Pirashvili, which I hope I cited in the lecture notes. Yeah, it is reference 19 on strongly perfect Lie algebras. There you see some duality theory between homology and cohomology. Maybe you can look it up there.
Thank you again, Professor Wagemann.
Thank you.